everyone, and welcome to a new episode of Inference, where we talk about programming languages and other funny stuff. Today, I'm incredibly happy to have here Vladislav Zavialov, which is a Haskell GHC Technical Steering Committee member and programmer at Serokell. Welcome, Vladislav. How are you?
Hello, I'm doing great. Thank you for having me here. So yes, I'm a software engineer at Serokell and the team leader of our GHT department. And Serokell is a software development company. It's remote first. We mainly use Haskell for our projects. I really like working here because it's a quite forward-thinking company. With the focus on professional and personal growth of its employees. For example, one time, one of our developers didn't know how to debug a seg fault, and our CEO, Arsenis Siroka, decided that our developers ought to know how the computer works at the low level, and we split our engineers into two groups, those who knew assembly and those who didn't.
Oh, that's amazing.
And the former half had to teach the other half assembly, yeah. And you can imagine how many man hours it took, and all of it at the company's expense. So there is a strong focus on making sure everyone is at the right competence level to do the job. And we do internal lectures. For example, I explained basic notions about programming to our non-technical personnel, so that everyone knew what a programming language and a compiler are. That's a few words about my company, where I work. About myself, in my free time, I like to do a lot of stuff. I'm not really good at any of it because there are so many things I just can't focus. Yeah, I can't help myself and stick to anything in particular. I like to press keys on the piano.
Oh, wow.
I wouldn't dare to call it playing the piano, but still, yeah, I find my favorite melodies by ear and kind of play them. I like electronic music and sound synthesis, so I compose stuff from time to time. Spending time outside, I love it. Riding a bicycle in the summer, skiing in the winter, running, hiking, swimming. I'm also sort of into medieval stuff. I do longsword fencing, Federschwert actually.
Okay.
I like learning languages. So English is not my native language, but I do enjoy practicing it. I try to do as much stuff as possible in English in my everyday life. And I started learning German recently. A couple of months ago, I got a dog, a Czechoslovakian wolf dog. So it's quite a serious breed, so I had to get into dog training. And I just keep finding new stuff to do. A week ago, I started playing chess.
Okay.
So yeah, I can't really keep doing the same thing for a long period of time. I mean, it's a blessing and it's a curse because I love it all, but I can't give it the proper time. And that's like outside work. There's also programming, which is an entire field of its own. There's so many fascinating things in programming languages and software design. It's also not surprising that one idea I like is having like a programming language with all the features like linear types, dependent types, row polymorphism. You just throw everything in, and because every feature it's got a certain use, and I'd like to have more features in my toolbox when I do everyday development.
And what is your favorite field in computer science? I mean, it's compiler design or web development. What is your favorite part of computer science?
So I think that the main thing that computers do is enable humans to achieve something that is not possible without computers. So they're augmenting our abilities. They help us, for example, when an engineer is trying to design a bridge, he can use simulation software to make sure that all the physical properties are right. And I really think that the main field of computer science is how computers interact with humans, so user experience. That's why I like working on interfaces, so trying to think about various data visualization methods, controls to manipulate the data. I like to create a structural editor, so we're using text editors. I think we can do better for programming, and programming languages as a consequence of that, because programming languages is how we tell computers what to do. That's how we get them to do what we need. And it's also a user-facing part of computer science. That's why I'm very interested in language design, type systems, with the focus on making it accessible to everyone. I'd like programming languages to be learnable. So every feature should be built on a solid core and create a cohesive whole so that developers can learn different parts of the language and immediately see how they can apply them for their particular domain.
Okay, great. And given that you're a member of the technical steering committee of the Haskell GHC, how did you start writing Haskell and why Haskell?
Okay, so when I was like 13 or 14, I was learning programming, and I wrote this huge program, 1,500 lines of code. I mean, it seemed huge to me at the time. And I had to present it to a large audience. There was a big screen and a huge hall full of people. And I was really proud about this program, and it crashed mid-presentation.
Okay.
So the next day I found the issue. There was a place where I forgot to close the file handle. And this was a really formative experience for me. I thought to myself, bugs in my programs, never again.
Okay, so Haskell was an obvious choice at this point, right?
No, it wasn't
Okay.
obvious at all. I didn't know about Haskell. So I started reading about best practices, trying out various programming languages one after another. Spent quite some time writing C++, C Sharp, Python, but none of them felt right because the best practices that I was reading about were immutable data structures, pure functions, and stuff like that. And I just couldn't express them well in the languages that I tried until I found Haskell, and it was so different. And it seems to me so much better with static types, immutable data structures, and lazy evaluation. It was the first language where the abstractions I built didn't feel broken. And there were so many concepts to learn, such as faults, functors, monads, monad transformers, and so on. And at last, these abstractions, they didn't seem so ad hoc. They seemed simple and elegant. But that's like an emotional statement. So I can't say that I chose Haskell for its technical merits. I was a kid. I liked Haskell, so I started writing it. And then eventually I invested so much time into it so that it's just a language that I know best. So it like another language pops up and it's better than Haskell in most ways. I don't believe that it can be better than Haskell in every way because there is always some trade-offs that you have to take. But if it's better than Haskell, then in most ways, that would be for me not a signal to jump ship and go to write that other language, but a signal to improve Haskell.
Yeah,
so
right.
we are as good.
Okay, that's a great thing. Given that you're working full time on the GHC, do you think that there is a feature that Haskell is completely missing today? If you had to say a feature that Haskell is completely missing today, what would you say?
I mean, I would say dependent types, but I mean, you are probably asking about something other than
Yeah,
dependent
maybe.
types, right? Yeah, okay. So it's hard to pinpoint a specific feature. There are plenty of avenues for improvement in the type system. Aside from dependent types, it would be nice to see extensible records with raw polymorphism, first-class existentials, parametric kind polymorphism, and unsaturated type families. Refinement types are also a good idea, and I wish they were shipped with GHC instead of a separate tool. There's Liquid Haskell, but it's a separate thing. And if you asked me a year ago, I would also name linear types and impredicative types, but now we've got them, so there's definitely progress. But it's hard to name just one thing that would be a game changer. There are like many developments that improve very narrow areas, not so much low-hanging fruit that if we had this thing, then Haskell would rock. No, I mean, we need many things.
Okay.
And there is no good, from the engineering standpoint, there is no good story for bootstrapping GHC from source. It's a self-hosted compiler, meaning that the Haskell compiler is written in Haskell. So to build GHC, you need a previous version. So then you need to build the previous version and then the one before and the one before and so on until you hit a very old binary. And it's actually like this old binary, the sources for it are lost.
Okay.
So you've got to trust this binary, and there is no way to get to a point where you've got like a C program. There is no C program from which you could bootstrap GHC. And to make things like completely terrible, the compilation in the earlier versions wasn't deterministic. So every time you run this bootstrap chain, you get a different binary with a different hash.
Okay.
Yeah, so you got to trust that your GHC is not compromised, and I think it's a very weak point which needs to be addressed. Yes, so if some company started to invest money into creating like a proper bootstrapping chain, I would be very glad to see that. And another problem, I suppose, is conditional compilation, because we in the Haskell land we are just using the C preprocessor with its if-defs, and the problem is that it operates on a completely wrong level of abstraction. It operates on text substitutions instead of like AST manipulation or something like that. And the result of that is that Turing has a very difficult time processing files which use the C preprocessor. If we had some sort of alternative to that, then it would definitely it would facilitate tooling development. And template Haskell, it could also be improved. So template Haskell is the way you do macros in Haskell, metaprogramming. And the problem with it is that there is no phase separation. So when you import some module, it's available both for metaprogramming and normal programming, which means that when you link your final binary, you will end up with libraries which you only use for metaprogramming, which you don't actually need at runtime, and you rely on link time optimization to get rid of them. And for cross compilation, it's also a problem. You can't use template Haskell properly when you cross compile. And when you're bootstrapping GHC at stage 1 of bootstrapping, you also don't have template Haskell for this reason. So better facilities for metaprogramming would be nice. I mean, what we've got already is like really nice. I like template Haskell, I use it, but we could improve it. The best way to see where people see avenues for improvement is to go to the GHC proposals repository. And there are plenty of good ideas. Like people suggest ideas, create extensive designs for these features. They describe the motivation, the specification for the proposed change, the effect that the change would have on the language, on the ecosystem, on the backwards compatibility story. And then everyone discusses it. So the GHC steering committee decides which proposals are accepted and which proposals are rejected, but the community shapes the proposals. So it's not just the author that writes a proposal. Everyone can comment and suggest their ideas, so that the author may or may not incorporate them into the text.
Yeah, got it. So thank you for the explanation. That was incredibly clear. You've mentioned dependent types, so we will be talking about dependent types. Would you be able to explain to people coming from other languages, maybe not functional languages, what dependent type are?
Okay, so dependent types are a feature of the type system. So if you use an untyped language, it's easy to write code that doesn't really make sense, and the compiler will not check it. You will find about it in your test suite when you run the program, but you don't get static guarantees of consistency and correctness of your code. So that's why we have type systems. But if you use a typed language, then you will eventually face the limitations of the type system. No one has designed a perfect type system, and I doubt it's possible to design a perfect one. You will always have some shortcomings, and you will face two sorts of issues. First one is that some valid programs are rejected. So you know your program is right, but you just can't convince the compiler that it is right. And the second issue is the opposite, that you wrote some code, it is not valid, but the compiler doesn't see an issue with it. So that's the two sorts of limitations that you have with type systems. The entire field of type theory is concerned with making more precise type systems which allow more valid programs and fewer invalid programs. And if you start with something very simple, such as simply typed lambda calculus, what simply typed means? It means you've got like your base types, for example, int, bool, then you've got the function arrow, and you can build types from these three building blocks. So you can have a function from int to bool, a function from bool to int, a function from int to bool, and stuff like that. So and that's just all the building blocks you've got. That's simply typed lambda calculus. And if you start writing programs in this language, you will very quickly discover its limitations because you will have to duplicate code. For example, you will need to redefine the type of lists for every element type. You would need to define the list of ints separately, list of bools separately, list of lists of bools separately, and so on, in potentially infinitely many types. And then once you define the types that you need for your particular application, you would have to redefine the helper functions that work on this type, like map, filter, and fold, the common list operations. You would have to redefine them also. You would get practically no code reuse this way. So when your type system is very simple, you will wish that it wasn't there.
Okay.
Yeah, so that's so one solution is to say, okay, type systems are not such a good idea, but and that's what the dynamically typed languages do. They probably, the authors of these languages, they had bad experiences with type systems, and they decided that they will design languages without this obstacle to the programmer, and that's a valid viewpoint. But something very important is lost along the way, and it is the consistency checking. I would like my compiler to actually understand my code, at least to some extent, and give me some hints about it, and identify parts of the program that I've messed up, and I mess up quite a lot. I mean, judging from the amount of type errors that I get every day, GHC is making a huge contribution to my code. There would be much more issues if I didn't have the help of the compiler. So what separates simple type systems from useful type systems? It's the amount and the quality of the type system features available to you, so you can express more complex concepts without redundancy. And the simply typed lambda calculus example, the solution to that is to introduce parametric polymorphism. So when you declare a list, you say, so list is not a type, list is a type constructor, and you have to specify the element type. You don't say list, you say list of int, or list of bool, or list of bool. And you define the list concept just once, but it has a parameter. The parameter specifies the element type. That's why it's called parametric polymorphism, because you've got a parameter there. And the reason it's possible is that the code and the memory representation are the same no matter what element type you use. That's how parametric polymorphism is different from, let's say, templates in C++. Templates in C++, they do copy-paste. The advantage of that is that you can generate more efficient code for certain element types, but the disadvantage is that you generate a lot of code and then maybe it will not get into the processor cache and you would get slowed down from that. So there are various trade-offs, no perfect solutions, but parametric polymorphism, there are many use cases for it, and it's great to have it in the language. There are many other features which are also helpful to reduce duplication of code, make more valid programs accepted, and fewer invalid programs accepted as well. So existential quantification, higher rank polymorphism, kind polymorphism, data type promotion, type families are all such features that are already present in Haskell today, and you can use them effectively to write more precise types for your code and make the compiler understand the structure of the concepts that you are that you have in your domain, in the domain of your application. And type system design is an active area of study. There is a constant stream of new great ideas and research papers about type theory. And dependent types are one such idea. And it's actually not a new one. The Calculus of Constructions paper, which describes dependent types, dates back to 1988. There is like definitely a lag between the introducing a concept and getting it into a semi-mainstream languages, because I will not call Haskell mainstream, but it's definitely more popular than some other languages. So semi-mainstream, Okay. And to understand dependent types, you will only need to learn two basic concepts, dependent products and dependent sums. If you've worked with algebraic data types in a language like Haskell or ML or Scala, you will probably know that understanding algebraic data types only requires understanding sums and products. So there are like two basic concepts, the sum type and the product type, and every other algebraic data type is built from these two basic building blocks. And in this sense, like the tuple and the either data types in Haskell are fundamental because they represent the core concepts of products and sums. And in the same manner, there are like two canonical dependent types. It's the sigma type, the dependent sum, and the pi type, the dependent product. If you manage to understand these two, then you've grasped the core concept, and then you can declare your own dependent types, because dependent types means that when you create your own types, when you declare them in your program to model your domain, you can create dependencies between your data and the types of other data. So that's a very abstract concept. If you want to make it like concrete, that's pi types and sigma types. You like read the formalisms, how these are defined, figure out how they work, and then you will grasp them. I don't think that this format of like a podcast or a video interview is a great way to introduce the formal concept, but I will talk a little bit on the abstract, vague concept of data dependencies. So the key idea is that the data that you have sometimes determines the type of other data that you have. For example, imagine a data record that describes a person, and you might have fields about nationality, age, and whether they have a driver's license, okay? But in Russia, you can't get a driver's license before the age of 16.
Okay.
So the record that contains Russian, 10 years old, true driver's license, true, it's an illegal value, an illegal state. And with dependent types, you would say that, well, if the nationality is Russian and the age is 16 or higher, then we represent the driver's license by a boolean. It's either there or not. But otherwise, we say that like it's completely missing. We use the unit type, which contains no information about the driver's license. And this way you can ensure that all the values that are constructible in your program are always valid. And the compiler will statically check it before you run your program. You will already know that you don't have messed up data.
Okay, got it. But don't you think that at this point people could, move the business logic from the function implementation to the function signature at this point?
It's a matter of engineering what you put in your type and what you put in your terms. But there's actually like a strict phase separation: what's executed during type checking and what's executed during runtime. So you've got control over that.
Okay.
You will probably want to execute during type checking only what is possible, and then if it depends on user data, something entered like into the input field, so you will have to process this data at runtime.
Okay. You previously said that the perfect type system has not been invented yet. I would like to ask you your thoughts about dependent type systems such as Agda, Coq, or Idris. And what do you think about those type systems, and what do you think that they are missing?
Okay, so these languages are great examples of languages that do have dependent types, but it doesn't mean that they have other features that are needed for practical software development. For example, I really like that Haskell has lazy evaluation and very sophisticated runtime to support it, because lazy evaluation, it is an unnatural thing for our hardware. The CPU and our RAM, they are not structured very well to handle this evaluation model. So we need to create like a virtual machine called STG. Haskell is compiled to STG, which is a lazy evaluation machine, and then there is a backend that translates STG to native code, but this backend requires a runtime system, and it's very sophisticated. And if you design your own lazy language, the main problem that you will face is that it will not be as fast as Haskell, because there's like a lot of effort put into making Haskell work fast despite lazy evaluation. Because on paper, lazy evaluation makes everything faster because you get better algorithms. But in practice, there is like constant factors that slow everything down. So maybe you've got better algorithms, but every step of the algorithm takes twice as much because you've got to dereference a pointer or something like that. And in the end, abstractly, lazy evaluation is beautiful. It's an absolutely wonderful concept, but practically it requires a lot of engineering to support it on the actual hardware that we have. And Haskell has that. Haskell has the runtime system to make lazy evaluation practical, which makes it very unique.
Yeah.
There aren't many other languages that do that. When the last time I tried writing Agda, it didn't have like the deriving mechanism. For example, in
Okay.
Haskell, I can write deriving ake, and I have the equality testing for my types. In Agda, I have to use the Emacs support to generate the boilerplate. And once I've got past 500 lines of generated code, I decided, okay, I'll check it out later when it got deriving.
Okay, got it.
Yeah, and there are other features, for example, parametric quantification. So there is a very important notion when you write a parametric quantifier in Haskell, you know that it will not inspect this value in any way. So it's irrelevant to your computation, and you get free theorems out of it. So, I mean, it's going to get pretty technical, but in Haskell, there's this class functor, and it's got two laws. And these laws are mathematical laws. So you've got to convince yourself that your code obeys them if you want to know that it is correct. And mathematicians, they came up with these two laws. But then it turned out that in Haskell, you only need to prove one of them, and the other one follows because of the way parametric polymorphism works in Haskell. And it doesn't work this way in Agda or Idris or Coq. So it's a Haskell specific thing that we can define our functors with less proving than in other languages. In Idris 2, I think they added this sort of quantification, but in Idris 1, as far as I know, it's not present, and in Agda or Cog, it's not present either. So that's parametricity, and there is the opposite thing, the lack of parametricity. So in Agda, whether you are parametric or not, it depends on the domain of quantification. If you are quantifying over types, you are parametric. If you are quantifying over anything else, you are not parametric. But in Haskell, this distinction is missing. You can be non-parametric over types, which is called type reflection. And you can, using type reflection, in runtime, check what types you have. So you can pattern match on it. You can branch on it, like a switch statement in C, and say, like, in case of int, I do that. In case of bool, I do that. In case of string, I do that. And that's built-in functionality. I mean, there is overhead associated with it, which is why you have to opt in. You have to write typeable in your type signature, but then you get it. In Agda, you don't get it. You don't have the typeable machinery. As far as I know, in Agda, there is no metaprogramming. Like the template Haskell alternative, there's no such thing in Agda. I mean, I think they've been working on adding it. They call it reflection, I think, but I don't follow it closely enough to say for sure. In any case, there are like certain things that Agda has and Haskell doesn't, and certain things that Haskell has and Agda doesn't. Likewise for Idris and Coq. Good example with Idris. So Idris 2 added linear types. Haskell also added linear types, but when Haskell did it, we also got multiplicity polymorphism, which Idris does not have. So that's like a Haskell specific thing, which like it's a nice concept. I haven't applied it yet because it's very new. I haven't written any programs with it, but I've read about it, and like it's a fun thing to contemplate, having multiplicity polymorphism. So instead of like identifying which language to use here, I think that there's great potential for cross-pollination. Languages should copy the good stuff from each other.
Absolutely.
And learn the lessons of what not to do as well. And that's why I'd like to see dependent types in Haskell, because even if Agda, Idris, or Coq have dependent types, these are different languages. And I see no reason why Haskell shouldn't be one of the dependently typed languages. It would be a great addition to it. I mean, I would add dependent types to Java if you let me, but that's a different story.
Yeah, absolutely. Maybe to Scala. It would be a bit easier for,
sure.
I feel like coming from an object-oriented background, let's say, or imperative background, working with dependent types can be a bit steeper, a bit harder for developers, or isn't it?
Well, dependent types are a very natural concept if you come from a mathematical background,
exactly.
because they do it without thinking about it. That's the norm there. Like depending on data, when you are specifying your type signature, like so what? Just do it. And programmers are conditioned into thinking the other way because we are often facing the problem of actually executing our code, and we are acutely aware of the separation between compile time and runtime. So it might be not easy to see with dependent types what happens at compile time and what happens at runtime. And it makes people confused. Like they say, how is it possible? How can you have a compile time guarantee for something that is actually only known at runtime? For example, how can you guarantee that your data is correct? How can you guarantee it statically if it's entered by the user when your program is running? Like it sounds impossible at the first glance, but actually what dependent types will make you do is they will make sure that you validate your data at least once.
Okay, got it.
So you get the input from the user, it may be problematic, then you validate it, and then you get the data structure which is known statically to adhere to all the invariants. So in a sense, dependent types is the compiler not forgetting that you did validation.
Okay.
It gets reflected in the type. So I don't see how object-oriented programming background would create problems understanding dependent types. It's just programming background in general that makes it challenging, because it's not really obvious how dependent types, which seem to mix your code and your types, how does that interact with the phase separation between compile time and runtime? But in reality, it's all figured out. It all works quite well.
Okay, got it. And I've also read an interesting blog post you wrote on the Serokell blog, and I will leave the link into the description of this video for everyone wanting to read it. And you were talking about Haskell Extended. So what is Haskell Extended?
Okay, so that's just a name I invented for using Haskell with many extensions. So GHC, the way it's engineered, it's meant to be a Haskell compiler, and Haskell is specified by the Haskell 2010 report. So we've got like a document that describes what the Haskell language is, but in reality, practically no one writes that language. Everyone is using certain extensions to the language which were added over time. So they are basically language features which you opt in, to which you opt in, and you have to specifically say in the header of your module or in your build configuration that in this code, in addition to normal Haskell, I use, let's say, GADT, type families, data kinds, polykins, and so on. So you say all that you use much more features than are available in the standard Haskell packaging, and GHC supports many such extensions. And in practice, you end up with quite a few of such extensions enabled in production code. But if you really like this, and if you really start adding many extensions and using them to the fullest extent possible, you can model dependent types in today's Haskell very awkwardly, very ugly and slow, but you get something like sort of that's the same thing that dependent types are supposed to do. And in my blog post, I basically explain that yes, it's possible, but do we really want to write the code this way? We should probably just add dependent types. And in the meantime, don't get too overboard with extensions. Everything has its limits before it breaks. And if you use them really actively with trying to push them to the limits, you will find the limits. You will find the GHC bugs.
Okay, and talking about Haskell extensions, before we had our recording session, I was talking with some friends in the Italian Haskell communities, and we were talking about the fact that sometimes it can be hard for people, which already have some Haskell background, to find the right extension for, achieving a certain result in an easier way. So, do you have any suggestion for people wanting to learn more about Haskell extension, where they can, look at documentation or understand which extension can suit their purposes?
Actually, not any good suggestions, because the way I did it is that I got obsessive about it and read the entire GHC manual.
Okay.
I just decided that I do not want to miss any extension in case I'll have a use for it in the future. Uh, and that's basically the two opposite approaches to solving any problem. It can be problem driven, so you've got a problem on hand and you're seeking the solutions. And from the opposite end, you can have a set of solutions prepared, but you don't know yet what problem they will come in handy for. The best strategy, I suppose, is to do both. You occasionally search the user's manual for things that you think might be helpful for your domain, and then at other times recreationally just read the user's manual and see if there are interesting things in it, and then later at work you will find use cases for it, like, aha, I read about it like a week ago, and what coincidence, I need
Yeah,
it
that's a
right
great
now.
suggestion, actually. Thank you. Okay, moving on to the conclusion for this episode, I would like to ask you if you have any idea on where we can see dependent types in Haskell ready for production.
I think at least several years would be a safe estimate, because um, there is actually no complete agreement that we want dependent types at all. It's actively being discussed by the GHC steering committee as we speak. There is like an email thread where concerns are voiced about the way that dependent types are presented and proposed, and maybe we want to do things a little bit differently. Maybe we don't want dependent types at all, or if we do, maybe the design that is being worked on right now isn't the best one. Maybe we
Okay.
want a different design for dependent types. Yeah, so it's being discussed. But at the same time, there are also things that are definitely beneficial for Haskell and will make dependent types, will make adding dependent types easier in the future. So I'm working on these things. So mini features which aren't dependent types yet, but when we get to adding actual dependent types, there will be a solid foundation instead of trying to add dependent types. For just one example, we could add visible dependent quantification, which is parametric, to Haskell today, and it will not be hard. I could do it like in a couple of
Okay.
months. Uh, and it will be helpful for adding dependent types later. It will be very helpful because it solves several syntactic issues and scope resolution issues. The problem is it's being discussed right now by GHT committee, who are saying, I mean, I'm on the committee, but I'm not the only person. Yes, and other people are saying that, well, maybe we don't want to add this feature because it doesn't fit really well with Haskell as it exists today. But I'm saying, well, it fits with dependent Haskell, which we want to add. But the response is that, well, we're not adding it yet. And with the language as today, it doesn't fit that well. So there is like a conflict between being forward thinking for adding dependent types and trying to optimize locally. So I will phrase it in the terms of local optimization and global optimization, because locally with Haskell that we've got today, if we did strictly incremental improvements, I would agree that we wouldn't want to do that proposal the way I did, and we wouldn't want to add it, because locally that's not the optimal solution. If we look globally, if we try to imagine a variant of Haskell that has dependent types, then my proposal makes a great deal of sense. Um, but I cannot execute on it based on my feeling like that it is right. Yes, I need to actually convince people that we want to go in that direction. So there are things that are a little bit contentious with regards to that. On the other hand, there are engineering things that I can do right now and that will cause no controversy at all, and which will also help dependent types. For example, I rewrote large parts of the parser, of the GHC parser, to make it more principled, uh, added some more elegant solutions which generalize nicer. And when it comes to adding dependent types, we will need to combine the grammars of terms and types into a single meta grammar. And with the work I've done on the parser, that will be easier. So there are social questions that need answering, like convincing people that we want to do dependent types and to do them in the way that we envision them. There are technical challenges of actually implementing dependent types, and there are technical challenges of making GHC internally more prepared for invasive changes. So doing different refactorings and cleanups to make adding dependent types easier. And right now, I'm focusing on the things that are not controversial, that are definite improvements to Haskell right now, which will also make adding dependent types later easier. And at the same time, while I'm doing that, I'm trying to write convincing GHC proposals that will clear up the design of dependent Haskell and will help people see that it is actually a good idea, because I do believe that. I do believe that it's a good idea.
Okay, got it. Thank you. So that was all for today. Thank you so much for being here. It has been a pleasure, and really looking forward to have you here for a new episode when the dependent type Haskell will come out, maybe in some years, but I really wish it can be earlier. Yeah, thank you again, and see you next time.
Thank you very much. Bye.
Thank you. Bye.